Hello friends, I am Professor ANIL Brahmin from Sri Sankachar Technical Campus, and in this video we will understand the displacement current density JD. If we want to define this displacement current density, we can take the very simple example of a capacitor in which here we are having two metallic plates and in between that we are having dielectric material. The basic property of the dielectric material is it is having dipoles in it. In metals, the flow of current is due to the flow of charges. Suppose say this is the voltage applied here, which means in the capacitor if we are applying this voltage V, the positive charges will be transferred with the help of wire to this metallic plates, and here also negative charges will be transferred to this metallic plates. Thus here in the metal the conduction current is existing and current density is denoted by JC, conduction current density, but here no transportation of charge is there, but the dipoles are oriented in a particular direction. Say for this case, this negative will be twisted like this and positive accumulated charge will be twisted. The accumulated charges which are displaced by a small distance is known as dipole. Thus orientation of these dipoles are changing, and thus in the dielectric a new type of current density, that is denoted by JD, known as displacement current density, is existing. And for deriving the expression of displacement current density, we must know the Ampere's law, del cross H equal to J, which is the point form of Ampere's law, and we must keep in mind the divergence of J must be equal to minus del rho V by del T, which is the continuity equation. And one more thing, which is the relation of rho V and divergence of D, which is from the Maxwell's first equation, divergence of D is equal to rho V. By keeping this thing, we can go ahead. Now if we are taking say del cross H equal to J, which is from the Ampere's law, if we will take the divergence of del cross H, which is now will be equal to divergence of J, this divergence of any curl must be equal to 0. This is the basic concept, because for any curly field if we will take the divergence, it must be equal to 0, but from the continuity equation divergence of J must be equal to minus del rho V by del T for time varying fields. Thus this expression is contradicting, which means for time varying field this del cross H must be having one more component which is similar to this conduction current density. Thus we can write del cross H equal to J plus G, which is a new thing which is to be defined. Now if we will take now the divergence of del cross H, we will get divergence of J plus divergence of G. This must be equal to 0. But as we are knowing, divergence of J is equal to del rho V by del T. Thus we can say this, if we will take divergence of J plus divergence of J equal to 0, we can write divergence of J equal to minus divergence of J, which is plus divergence of rho V by del T, which may be written as d by dt divergence of D, because rho V from the Maxwell's equation must be equal to divergence of D. Thus by comparing these equations, this divergence of G must be equal to divergence of del D by del T, which means G must be a new quantity which is equal to del D by del T, and this new quantity is defined as displacement current density. And this is all about the derivation of the displacement current density, as by keeping three things in mind we can derive it. First is point form of Ampere's law, del cross H. Then by remembering continuity equation, divergence of J equal to minus del rho V by del T, and Maxwell's equation, which is first equation, which is divergence of D must be equal to rho V. Thank you.